Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
Conditional statements are a big part of geometry, and we can actually prove and relate all the different items with a conditional statement as to be a way of stating it true or false or things like that. Conditional statements are also big in programming. You can have if-then statements, if-else statements. So if you're somebody who likes the IT world, you might be doing a lot of conditional statements in your future. But you've probably used them in your real life already. Your parents or whoever lives in your house, that person in charge of you that makes all the rules. If, notice the word if, that's why it's conditional. If you clean your room, then you can go to the game. Okay, so with this conditional statement, it's an if-then. So we have a hypothesis and a conclusion. Now, conditional statements can be written without the word if and then. You just have to readjust your language. When you clean your room, you can go to the game, right? But the big idea is that in this case, the hypothesis was cleaning your room. And the conclusion was go to the game. And a lot of times the hypothesis gets called P and the conclusion gets called Q. So if P, then Q. That would be the ideal way of saying that. So there's your kind of math symbols, because we don't always like writing hypothesis, conclusion, and the if and the then. So I'm going to make a statement that is not an if-then form, and we're going to turn it into a conditional statement. All equilateral triangles are equiangular. There's a statement. It doesn't have a hypothesis conclusion that we appear. So how could I turn this? Okay. There's a couple ways we could do it actually, because this happens to be true in multiple formats, but if you are given an equilateral triangle, so see how I talked about the equilateral triangles? Then it is an equiangular triangle. Now we've written it in if-then form, so now we can clearly see our hypothesis and our conclusion. I forgot my U. There we go. So we need to be able to find out whether these statements are true or false. Okay? So it's called a truth table, is what they do. So again, P is your hypothesis. Q is your conclusion. And this would read P, then Q. So are these items true or not? Okay. So P could be true. Q could also be true. P could be true, but Q could be false. P could be false and true, Q could be true, or they could both be false. These are the only 4 ways that this could happen. Okay. If you clean your room is true, then you can go to the game. So if your room is clean and you went to the game, is that a true statement? Absolutely. Okay. If you clean your room, then you can go to the game. Okay. Well, if you cleaned your room and then they didn't let you go to the game, is that telling the truth? No. Okay. Well, if you didn't clean your room, then it doesn't matter about the conclusion. You're not going to the game. So these are okay. And that's how the computer is going to read it. Okay? So think of it this way, maybe not so much with the game. If it rains, then I will bring my umbrella. Okay, so I want you to think, can you catch them in a lie? It rained, then I brought my umbrella. They told the truth. It rained, but I didn't bring my umbrella. There they told a lie. It didn't rain, but I brought my umbrella. Well, they only said that they were guaranteeing their umbrella if it rained, so they didn't lie. It didn't rain, and I didn't bring my umbrella. Still, they didn't lie. So when we think about true or false being, did they lie? That makes a little more sense. So keep in mind that that's what happens with a truth table. Is it's just saying, hey, did they lie? The only way they're going to lie is if it rains and they did not bring their umbrella. All the others, at least, we don't know what they're going to do if it doesn't rain. They didn't tell us that. They only told us about what would happen if it rained. Kind of like if you clean your room, you can go to your game. Now, we know most parents are, probably, if you don't clean your room, you're not going to the game. But they didn't say that in that first conditional statement. They only said, if you clean your room, we will let you go you're going to the game. They never said what would happen if you didn't clean your room. So they let you go to the game anyways. Well, they were super nice. Maybe you did something else. Who knows? We don't know what happened in that situation. They only discuss what would happen if you cleaned your room. So conditional statements can only judge the outcome as true or false based off the hypothesis. Did the conclusion follow the hypothesis? It can't come into, well, there was this one time. Well, now we're violating our original condition. Maybe it was just a condition for that day. Okay. If a quadrilateral has a right angle, then it is a rectangle. So what are they talking about? Okay, well, quadrilateral means 4 sides, so we need to have 4 sides with a right angle. Okay, 4 sides, 1 90-degree angle. That's our hypothesis, and our conclusion is it's a rectangle. So can we guarantee that this is true? Let's think about it. Let's look at a right triangle. And I know you're going to right triangle. Seriously? That has 3 sides. You're right. I get it. We're going to take this right triangle. And we're going to cut the top off. Once we cut the top off, we have a 4-sided shape. Wait a second. It still has a right angle, right? is it a rectangle? No. We found something that made this true and this false. So that showed that the overall statement was false. We found a proof by counterexample. Okay, so we're able to show that if you found a true statement, then a false statement, we were able to show it was false. Okay, so other conditionals, other statements. So we have our original statement. P, then Q. Okay, that's our conditional statement. And it's conditional because it's only going to work in certain scenarios. It doesn't work 100% of the time. Okay, so now we have the converse. And when we talk about a converse statement, I think reverse. If I reverse that, Q, then P. Well, now sometimes that's true when the conditional is not. Let's come back up here. If it is a rectangle, then it is a quadrilateral with a right angle. Yeah, in fact, it has 4 right angles, right? Okay. If I bring an umbrella, then it rained. If I clean my room, then I go to the game. So see how that's reversing all those statements. Okay. Inverse. Inverse basically means not or opposite. So not P, then not Q. So this little squiggle means not. So if it is not a rectangle, or if it's not a quadrilateral with a right angle, or if I don't clean my room, then I don't go to the game. If I don't bring an umbrella, then it doesn't rain. Well, I don't think that ever worked out for anyone. Just because you didn't carry your umbrella doesn't hold off the rain, right? So no one said the inverse is always true, but that's something to think about. And the contrapositive. This is when everything's backwards. Not Q, then not P. If I don't go to the game, then I didn't clean my room. So see how it's completely backwards? Okay, so it's inverted. So it's reversed or converse, right? And inverted. So everything's all sorts of backwards. So we can write these statements in the different formats, and they may be true or they may not be true depending. Okay? So we're going to look at one of these, okay? And remember, if you have something that's biconditional, okay, biconditional, that means you're looking at the statement and the converse, both directions, and they'll put that. Okay, now, P, Q, true, true, false, false, true, false, true, false. Okay. So, if it rains, then I bring my umbrella. If I bring my umbrella, then it rains. Yeah, that's true. If I bring my umbrella, then it didn't rain. If it didn't rain, then I brought my umbrella. Well, one way works, one way does not. Okay, and I can show this with some different numbers, but this is how it turns out to be true, to work. Okay, so there were 2 truth tables that technically I went over here. And we will look at an example where we write all the statements down and we talk about the conditional statement versus the biconditional statement. So really these truth tables are not a big important part usually in high school geometry, but if you're going to go on to discrete mathematics at the university level, you're probably really going to be looking into these truth tables, and you really want to make sure you understand what these statements mean. Okay, so let's look at some of these conditional statements. We'll look at the conditional, we'll look at the converse, we'll look at the inverse, we'll look at the contrapositive, and then we're also look at the truth tables. So the product of two numbers is negative. Okay, so our P is given two number. You have two numbers, right? And Q is if you multiply and you multiply them, then Q would be, then the answer is negative. Okay. If you multiply two numbers, then the answer is negative. Okay, so we're going to look at a statement, and we're going to look at its inverse, its converse, its contrapositive, things like that. So if you multiply numbers with opposite signs, I forgot to say two numbers with two numbers. If you multiply two numbers with opposite signs, then the product is negative. So we're going to look at the truth table. Okay? So if P, and that's that two numbers with, so multiplying two numbers with opposite signs, that's P. The product is negative, that's Q. And we're going to look at P, then Q. So true, true, false, false, true, false, true, false. Okay. So multiply two numbers with opposite signs. That would be like 5 times negative 3. The product is negative 15. Is that negative? Yes. So this made a true statement. Okay. Multiply numbers with opposite signs. The product is negative. Well, that's true, not false. So we can't, this doesn't match up, right? This was true, but this isn't false. This is still true. So that's why this is a lie. Okay. Now, it doesn't tell us what happens down here. Okay? So we know what happens if this is false, but the conclusion only could start this. So because the first part is false, we can't do anything about the conclusion. Okay? So yes, it's kind of weird that we still have to say true and true. We know this one we know we're kind of iffy about, right? Because we didn't have a result for when it's negative. However, if I say the product of two numbers with opposite signs I'm shorthanding so I can save you time there, is, let me reword that. The product of two numbers is negative if and only if the numbers have opposite signs. Now we're saying this is biconditional. We're saying if you have P, then you get Q, and if you have Q, then you get P. Oh, so let's come back up here and think about this. P, then Q. Well, five times 3 is positive 15, right? Negative 5 times negative 3 is also positive 15. Okay. So here, they're saying if you multiply two numbers, if they have opposite signs, the result is negative. If they don't have opposite signs, the result is not negative. They're going both ways here. Okay? So we're supposed to use, okay, so think about that. Okay, same signs. Okay, so this is definitely true. If they have different numbers, then they're negative. If they're negative, they have different signs. Check. Okay. If they had different numbers, but they're not negative. Okay. So here, this is saying Q is supposed to be false, but Q is true. Okay. Negative 15 is negative, but these don't have opposite signs. So while this was true, this was not matching our perfect statement, so we can't do that. So if this should have been positive, right? So this is not negative, this is not opposite signs. Okay. So you can, it's a bit confusing. I get it. I understand. A lot of times you can just kind of think, are we saying a true statement? If they have different signs, then the result is negative. If the result is negative, then they had different signs. False would be positive. So if they're positive, then they had different signs? No. Okay. If they had the same signs, then it's negative? No. If they had same signs, then it's not negative. Oh yeah, that works. So we have to be careful with how we say it, and we have to be really careful because the computers, when we go to do true statements with computers, they don't necessarily understand it. Okay? So, and then we're going to write a conditional statement. And I'm not going to worry about the truth of it. We're just going to write the conditional statement. If you are at least 18, then you can vote. Okay? So the converse of that. If you can vote, then you are at least 18. Now the inverse of that. If you are not at least 18, then you can not vote. And the contrapositive. If you cannot vote, then you are not at least 18. And again, these truth tables, like I said, we can utilize them with computer programming, and that's really their biggest place that they have value, because the computer's not going to be like, ooh, well, there's this one person that's at least 18, but they never registered to vote and they can't get to a voting place because they don't have a car. The computer's not going to logic that out. That's adding in extra variables. So when we're working with truth tables, it really is to get to black and white without bringing in other elements, because a computer cannot do that. So this is really big in coding. So truth tables, I'm not going to go into them more really with my videos, but if you're going into different programming classes, or maybe you're going to be going into discrete mathematics, then you're probably going to want to check them out a bit more.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.